Hello. Today we continue solving problems on the relativity of mechanical motion and proceed to the solution. The pilot of an airplane wants to fly strictly to the north, but the wind blows to the west at a speed of 36 kilometers per hour. In what direction should the pilot direct his plane if its speed relative to the air is 350 kilometers per hour? Draw the vector diagram for the previous paragraph. If the pilot decreases the speed of the airplane, should he change the angle obtained in the first part of the problem? Let's write down the condition of the problem and look at its solution. We will need to determine the direction in which the pilot should move, that is, to direct his airplane. We will understand the direction as a certain angle, denoted by the letter alpha, and the wind speed is known in this case. Let it be the speed v1 equal to 36 kilometers per hour. And we also know the speed of the airplane itself. Let's call it v2, 350 kilometers per hour. The vector diagram demonstrates how we will combine these vectors and the resultant vector that we obtain. Additionally, we can determine the angle at which the pilot should direct the airplane in order to travel directly north. Moreover, let's examine the necessary action the pilot should take on the same diagram to decrease the speed of the airplane, whether it involves adjusting the angle or not in this scenario. First of all, let's put the direction of the sides of the world, and so we've got northeast, west and south, and the pilot's job is to fly north. The wind speed in this case is directed, let's put it like this here, it's v1 to the west. And now if the pilot initially directs his velocity vector to the north, it is clear that the wind speed will be added to it, and with the sum of these velocities he will be traveling approximately to the northwest. Therefore, in order to compensate for the wind speed partially, he has to take a little bit to the east. So the pilot's speed is going to be directed at a certain angle to the northward direction, and that's going to be the v2 speed, the actual speed of this airplane. And when you add to that the velocity of the wind, we should get the resultant velocity, which will be pointing strictly north. That's let v3. That is, from the point of view of the diagram, we have a right triangle in which the hypotenuse is the actual speed of the airplane, and two cathetes. One of them is the wind speed, and the second is the total speed of the airplane relative to the ground. The expression that can be written down here will look like this. The full speed of the airplane is the actual speed relative to the air plus the speed of the wind itself. That is their sum. Vector allows us to construct such a triangle. So, the diagram itself is obtained, and now we can start to find the angle. The angle in this case, we're going to be looking in the direction of north. This is the so-called azimuth, that is the movement in relation to the direction to the north. In order to find this angle, we must look carefully at the triangle. Look at what we know in this triangle. Here we know the hypotenuse and the opposing cathetus, from which we can conclude that through the sine of the angle alpha, we can relate these two sides of the triangle. So, the sine of this angle will be equal to the ratio of the opposing cathetus, which is v1, to the hypotenuse, which is v2. And we actually write down the expression from here. The sine of this angle is 36 kilometers per hour divided by 350 kilometers per hour. Note that here it is not necessary to translate these speeds in c, because when dividing they are still reduced, so you can leave the speeds in kilometers per hour. So after the calculation we get a sine of approximately 10.29, and calculating the arc sine from this number, we get an angle of about 5.9 tenths of a degree. Therefore, the pilot must precisely determine the angle at which to control their velocity. Should he adjust the angle if his speed decreases? Asking the previous question, when speed decreases, should a change in angle be made? Let's look carefully at this diagram and think about what happens to the angle if we decrease the velocity of V2. For one remains the consistent constant. Well, if we compare this situation, that when fulfill the condition, we have accurately formed this triangle into a right triangle, maintaining its original form and ratios, all while staying true to its proportions. But if we reduce the hypotenuse, so V2 becomes smaller, here's its new value, and we add to it the wind speed, which has not changed. That is, in such a way we transfer this vector parallel to it, then the total speed of this airplane in the end is directed not to the north. And it turns out that the pilot will have to make this angle larger as his speed decreases. And when we add the corresponding velocity, we get the fulfillment of this problem again. So the answer is that if we want to reduce the speed, then the angle will have to be increased. This is how such vector diagrams help to analyze problems where we consider movements in several directions and several bodies at the same time. This is my farewell. I will see you in our next lessons. Goodbye.